In this video, we are going to continue looking at mechanical vibrations oscillations, which are an application of the second-order linear non-homogeneous differential equations with constant coefficients. In the previous video, we addressed these vibrations, but we only looked at the case when this external force, capital F of t, was equal to 0. This video, we will remove that restriction and consider a driving force. And just to review, we're looking at a periodic external force that is applied to a spring mass system. Here our F of t is our external force, m here is our mass, u is the displacement of the mass from its equilibrium position, this lambda is our damping coefficient, and the k is our spring constant. And then because we're looking at periodic external force, we're going to take this form of the equation, the mu double prime plus lambda u prime plus ku equals f naught cosine of omega t. A couple things to note: omega t is the frequency of our applied external force, and then the mass, the damping coefficient, and k, the spring constant, are all constants. So here we have a second-order linear non-homogeneous differential equation with constant coefficients. We will solve the second-order differential equation using the regular way that we solve second-order differential equations that are non-homogeneous with constant coefficients. And then we will solve it first in a problem, an example problem, and then we'll solve it in general. And we'll come up with a solution, and then we will, like the other video, we will put it in this form, this r cosine omega t minus delta. Our book assures us that the calculations for this r and the cosine of delta is merely algebraic, but it's quite lengthy and cumbersome. And for that reason, your book did not cover the algebra to come up with these formulas, and neither will I. But these are the formulas that you will want to either remember, or hopefully you have a cheat sheet for yourself. Once we have our solution in this form here, we will look at the three different cases for comparing omega, that's our external force, the frequency of our external force, and then the natural frequency of our spring mass system, omega naught, which is equal to the square root of k over m. So if omega is small compared to omega naught, we'll see that after the initial transient response is damped out, the remaining steady state response is essentially in phase with the excitation, and the amplitude is somewhat larger, sort of like this graph here. We have, our solution in blue is approximately the same in phase with the forcing function. However, you can see the amplitude is a little bit larger. And then we have some other calculations. And this is actually, the calculations in the graph is from an example we will do in this video. The second case we will look at is when omega, the frequency of our external force, is equal to omega naught, the frequency of our system, our spring mass system. And we'll see that this is the resonance case. And that's where even a small force can give us a really large amplitude increase, right? The amplitude of the steady state increases many times the static displacement. And the predicted phase lag of pi over 2 can be seen in this graph. And also we can calculate that here. Again, these are from an example we'll do in the video. And you're familiar with resonance, like if you've ever pushed someone on a swing, if you push and it's with the same frequency as the swing, then you'll be able to get someone to go higher. Our last case we look at is when omega for our external force is large compared to omega naught, the natural frequency of our spring mass system. And we'll observe the amplitude of the steady forced response is a fraction of the static displacement. So here our solution is not as big as our forcing function. And the phase difference between the excitation of responses is approximately pi. And then there's one more overview slide. We're going to talk about forced vibrations without damping. And since we don't have damping, our gamma over here that multiplies u prime is equal to 0. So that term goes away, and we have this simplified equation. We can talk about forced vibrations without damping by looking at our previous equation, our full equation, with mu double prime plus gamma u prime plus ku equals this over here. Except that the simplified form allows us to convert to this form here, which gives us some other phenomena we can explore. And the first one is beats. And that's when the forced frequency is not equal to the natural frequency. Then what we have is our solution here is we have a faster oscillating part of the solution with a slower oscillating part of the solution. And what that gives us is this kind of form here, the beat, where we have a fast oscillation, but kind of overarching that fast oscillation is kind of this other oscillation that's going on as well. And then, of course, when omega is equal to omega naught, or forced frequency is equal to natural frequency, we can look at resonance and we can look at it in another way. We are going to start by looking at forced vibrations with damping. So we have this second order differential equations because we're also going to assume our forced vibrations are done with a periodic force. So the first example is the motion of a spring mass system satisfies the differential equation u double prime plus u prime plus 5 force u is equal to 3 cosine t. And we have u of 0 is equal to 2, u prime of 0 is equal to 3. We want to find the solution of this initial value problem and describe the behavior of the solution for large t. And this is just as we would solve for any non-homogeneous second-order differential equation. The first step is to solve the homogeneous equation. And we have u double prime plus u prime plus 5 fourths u is equal to 0. Again, we're doing the homogeneous equation. We look at the characteristic equation and see that r is equal to negative 1/2 plus or minus I. So our general solution for the homogeneous equation is e to the 1/2, negative 1/2 t, plus c1 cosine of t plus c2 sine of t. Next, we need a particular solution of the non-homogeneous equation because this the force or the g of t over here on the right side of the equation involves a cosine. We would use undetermined coefficients, and we assume that y, our particular solution, has the form of a sine of t plus b cosine of t. I have the solution here, but I also do have kind of the steps listed out here. So if g of t is sine of b of t or cosine t, then we assume y is a linear combination of sine and cosine, which we have here. And then we take the first derivative, which is here, the second derivative here. We plug y prime, and y double prime into our differential equation, and then we can solve, as you see, for our coefficients a and b. So what we get is y of t is equal to 48 over 17 sine of t plus 12 over 17 cosine of t. And now we can come up with the general solution of the second order non-homogeneous equation by first adding the general solution of the homogeneous equation plus the particular solution of the non-homogeneous equation together. We can then solve for the C1 and C2 by using the initial value. And here we have the solution for u of t. Remember, u is the displacement from equilibrium. And that consists of the solution to our homogeneous equation plus the particular solution of our non-homogeneous equation. And generally, we view these two, this part here we view as the transient solution. And the reason why it's transient is you notice that we have this exponential to a negative power. That means that it's an exponential decay. And so this part of the solution will decay rapidly and approach 0. So the transient part comes from the solution to the homogeneous equation and is needed to satisfy the initial conditions. On the other hand, this part here that comes from the non-homogeneous equation is called the steady state. And the steady state represents an oscillation that continues indefinitely. And the steady state solution is the particular solution of the full non-homogeneous equation. And after a fairly short time, the transient solution is vanishingly small, and the full solution, u of t, is essentially indistinguishable from the steady state. And again, the steady state solution represents a steady oscillation with the same frequency as the external force that is applied. With increasing time, the energy put into the system by the initial displacement and velocity is dissipated through damping, and the motion then becomes the response of the system to the external force. Without damping, the effect of the initial condition would persist. Here I have the steps for solving a second-order non-homogeneous differential equation with the solution here underlined. However, like the previous video, we like our solution to be in this form where it's easy to read off the amplitude measure, the frequency, and the phase shift. And your book assures you that from some straightforward but lengthy algebraic computations, we can find that R here is equal to F naught over delta, where delta is equal to the square root of m squared times omega naught squared minus omega squared squared plus gamma squared omega squared, and that cosine delta is equal to m over omega naught squared minus omega squared over delta, and we have a formula for sine of delta is equal to gamma omega over delta. And then, of course, just a reminder that omega naught, that's our natural frequency of our spring mass system, is equal to square root of k over m, or omega naught squared is equal to k over m. Your book does not give you the calculations and algebraic calculations to solve for r and delta, and neither will I. We are simply going to take the formula and use it. It is an important formula. We are not going through the derivation because it's really too lengthy. It's not something you would do during an exam, but it is an important formula to know. So I've written that over here, the results of the formula here for our reference. And we'll look at this formula to look at resonance, and in particular the relation between R and the frequency of the external force. Remember, R is sort of our amplitude measure, and so for resonance we expect a large R, and it has something to do with the frequency of the external force. Of course, we already kind of said in the introduction that we want to match that omega over here. And before I continue, I'm just going to say this chapter, and I think it's noted at the beginning of your chapter in the book, this chapter has a lot of algebra and calculations, and it's stuff that really you wouldn't want to have to rederive during an exam. I do have, some things, the algebra I kind of skipped, as I already told you, calculating R and delta, but many of the calculations I'll do for you, but I won't explicitly go over them, but you can pause the video and look at them if you'd like. But this is my warning. There's lots of algebra in this video, but you don't want to get bogged down. Make sure you keep an eye on what the points are, what the point of all this calculation is. So often when we look at resonance, we look at the ratio of R, the amplitude, versus F naught. So we compare. So often it's a comparison of what kind of amplitude increase do we get given a small force. So if we have a small force that can give us a large amplitude or increase our amplitude by a large amount, that's when we say we have resonance. So we're comparing R and the force. So this is why we have this ratio here. The K gets multiplied in. I'm not sure why we do that, but there you go. Often it's RK compared to F naught. And then just looking at this formula here, so R is equal to F naught over delta, that means RK is equal to K times F naught over delta, which means RK over F naught is equal to K times delta. So that's what we have here, K, and then our delta is the square root of this m squared omega naught squared, this part here, which I have written here, our m squared, our omega naught squared minus omega squared plus gamma squared omega squared, all raised to the negative 1/2, just because it's underneath the fraction here. So I have the negative 1/2 here. Now I'm just going to look at this portion here, what's in the square root. I've rewritten it here as m squared omega naught squared minus omega squared squared plus gamma squared omega squared. And I did some algebra, and you can take a look at this, and I finally, at the very end, came up with k squared, and then I have 1 minus omega over omega naught squared plus gamma over m, k times omega over omega naught squared. So when I plug it back into this formula, what I get is RK of F. I just multiply over k on top, and then I get this, this fraction here, which we will be looking at. Also, often we have this capital gamma is equal to lowercase gamma squared over mk. These are kind of the lowercase gamma, the m, and the k. This is all the different things that make up what really happens with damping. And that's, so we combine them together and call it capital gamma, which is our damping parameter. So I've summarized the things on this top half here for our reference. I have our solution to our second order differential equation here, and then here I have the ratio of the RK to F naught. And we are going to consider 3 cases for omega for the frequency of our force. First, we're going to look at low frequency excitation. That is when our omega is close to 0. Then we'll look at fairly high frequency excitation as omega approaches infinity. And last, we'll look at an intermediate value of omega. We will start with low frequency excitation when omega approaches 0. So over here, you'll see that this will go to 0, this term will go to 0. And what we get is RK over F naught, now this multiplies this, is going to approach 1. Or in other words, R is going to approach F naught over K. And if you recall, F naught over K, that's equal to, by Hooke's law, is equal to L, our initial displacement. Now we'll look at high frequency. As omega approaches infinity, you can see that this will get really large and this will get really large. And you have to remember this is to the -1/2. So our R will start to approach 0. So if we don't have a super low omega, we don't have a super high omega, we have some intermediate value of omega, the amplitude will have a maximum. And to find this maximum, we can differentiate R with respect to W and set the result into equal to 0. In this way, we find the maximum amplitude, omega max, is equal to omega naught squared minus gamma squared over 2m squared is equal to omega naught squared times 1 minus gamma squared over 2mk. So we want to note here, looking at this, omega max is going to be smaller because we take omega naught squared and then we subtract stuff. So omega max is going to be smaller than omega naught. And omega max is close to omega naught when this gamma here is small. Plugging in omega max for our omega, we get R max is equal to F naught over gamma omega naught times the square root of 1 minus gamma squared over 4km, which is approximately equal to F naught over gamma omega naught times 1 plus gamma squared over 8mk. So what we have for small gamma, when we don't have a lot of dampening, our max is approximately equal to F naught over gamma omega naught. So that means when omega is near omega naught, then the amplitude here, our max, can get quite large, even if the external force is small, just because this gamma is very small. So the smaller the value of gamma, the larger the effect. As I had mentioned, our capital gamma is a better measure of our damping. It takes into account not just our damping parameter, but also the physical characteristics of our system, M and K. So here we have a graph, and it talks about the ratio of omega to omega naught. So 1 is where omega is approximately equal to omega naught. Below is where omega naught's larger, and above is where omega naught starts getting smaller compared to omega. And we graph that compared to our amplitude over our force. So it's our ratio of amplitude to force. So we want to know, can a small force give us a large amplitude? One of the things to notice is at this gamma equals 0.15625, you can see where omega is equal to omega naught, or we have the ratio is equal to 1, you can see that there's this sharp curve. In other words, it becomes asymptotic because our R can get very large. And then, of course, as R goes to 0, you have this complete asymptotic behavior. And we have this also, we can bring down this calculation here, setting gamma equal to 0. So we just have r is equal to f naught over m, omega naught squared minus omega squared. You can see, again, why this asymptote comes about when omega is equal to omega 1. And also, so this comes about when omega is equal to omega 1 and as gamma approaches 0. So the short note here is as gamma, capital Gamma, approaches 0 and omega approaches omega naught, we can get this asymptotic behavior. Again, that is our resonance behavior. We're going to do an example like with a particular differential equation, particular like real solutions, real numbers. But before we get to that particular example, there's one other thing we're going to look at, which is the phase angle. Also depends on an interesting way on omega. If our omega is close to 0, then our cosine delta here is close to 1, and also sine delta is close to 0, which means that delta is equal to 0. So the response is nearly in phase with the excitation, meaning they rise and fall together. And when omega is close to omega naught, then cosine delta equals 0, and sine of delta is approximately 1, meaning delta is approximately pi over 2, which means the response is delayed by pi over 2, later than the excitation. And for very large omega, then we have cosine of delta is close to negative 1, sine of delta is close to 0, so delta is close to pi. So the response is nearly out of phase with the excitation. Again, we'll see a particular example with numbers, and we'll also see how the phase angle changes. And here we are with an example to kind of bring together those ideas we just talked about abstractly. So we had the u double prime plus 1/8 u plus 1u is equal to 3 cosine omega t, where u of 0 is equal to 2 and u prime of 0 is equal to 0. We're going to show plots of the solution for different values of the frequency. One, we're going to do a low frequency, low compared to our natural frequency omega naught. And then we're going to do where omega is equal to omega naught. And then last, where omega is greater than omega naught. And we're going to compare them with corresponding plots of the forcing function. And I started, actually this problem we had when we did a long time ago, when we did homogeneous differential equations. So I went ahead and just put that solution up. For the homogeneous differential equation, we have this characteristic equation, we had this general solution, and then without forcing, we can solve for the C1 and C2, or A and B in this case. And this was our solution, that u of t is equal to well, this was our general solution, and we rewrote it into this form where we have an r, an e to the t cosine of omega t minus delta, where our delta is given to us by this equation here. And this was the graph. Next, I was going to solve the non-homogeneous differential equation. I was starting here, and then I realized, you know what, I'm just going to use these formulas because that's what they're there for. Here I have my differential equation, u double prime plus 1/8 u prime plus u equals 3 cosine omega t. I'm going to look at this compared to my general form here. So what I get is my mass is equal to 1, my lowercase gamma is equal to 1/8, my k is equal to 1. My f naught, that's the coefficient in front of cosine omega t, is equal to 3. My omega, I'm going to vary that omega because they wanted different values for the frequency. So I'm going to vary omega. My omega naught then is equal to square root of k over m. Just this is the formula to remind you here. So k over m is just 1 and 1, so omega naught is 1. And then my gamma, my capital gamma, over here to remind you, is equal to lambda squared, which is 1 over 64 divided by m times k, which is 1. So it's just 1 over 64, which is approximately equal to 0.015625. And then my general form of my solution, u, that's my displacement, is equal to r cosine omega t minus delta, where r is this long formula here, and we have a formula for cosine delta. So I started plugging into my delta. So I have my delta is equal to m squared. M is equal to 1. Omega naught squared minus omega squared. So omega naught squared is 1 squared minus omega squared. I chose 0.3 as my first omega naught. I wanted The first case I wanted was an omega not smaller than omega. So I chose 0.3. That's where that came from, squared, plus gamma squared times omega squared. That's 1 over 64 is our gamma, and my omega naught is 0.3 squared. I calculated that and I got 0.9177. So R is equal to F naught over gamma. That's 3, our F naught over gamma is equal to 3.29. Our cosine of delta is equal to, according to this formula, m, which is 1. Then I have my omega naught squared, so that's 1 minus omega squared. Again, I chose 0.3 for my omega. And then over delta, and I get cosine of delta is equal to 0.992, so almost 1, which means delta is almost 0. And my general solution for u is equal to, what do we have? R cosine omega t minus delta. So that's R, which is 3.29 times cosine, and then what, omega t. So our omega we chose is 0.3 t minus, and then our delta, where's our delta here? 0.0412. I have my graph here, which I'm sorry if it's not quite accurate, but I tried my best. It's something like this. And then my comments here, and also that other graph we did in the previous slide when we were just talking in general. Here is the gamma, that's exactly the gamma that is for this case here, 0.01562. So we're on this curve, no, we're on this outer curve. So for low frequency omega, so our first omega was 0.3. It's supposed to be small compared to omega naught. After the initial transient response is damped out, the remaining steady state response is essentially in phase with the excitation. So you can see they're kind of in phase. I meant to draw them in phase. And the amplitude is somewhat larger. So I should have amplitudes that are somewhat larger. Looking at this graph here, again, we're on this curve here for gamma is equal to 0.15625, and our omega naught over omega, since our omega is smaller than our omega naught, is somewhere over here at 0.3. So you can see that our amplitude might be a little bit larger, but this is where we are on this graph for our ratio of R to F naught. So it's a little bit larger than 1. Here I did the same thing, but now I chose omega naught equals to omega. Remember I was going to do, it said to do different solutions for the frequency, so I chose 3. So here I have omega equals omega naught. I did the same calculation for R and delta, and then, my capital delta, and then my lowercase delta. And then I have my graph here, and my comments. The amplitude of the steady state response is 8 times, right? If you look at R, the amplitude is 8 times the static displacement, and the predicted phase lag is pi over 2. And again, we're on this curve here. And our omega over omega naught, in this case, is close to 1. And so this is where we're going to have our solution growing, theoretically to infinity. The last case that we are going to look at is now when omega is equal to, what did I choose for omega? Someone tell me, show me where my omega is. Omega is equal to 2. So it's twice what omega naught is. And again, that's kind of like to show some high frequency excitation. You can see I calculated delta, I calculated my R, and I calculated my my phase. And here's my graph. Actually, this one was hard to do, but they're supposed to be out of phase. If you look at the troughs of the blue, it's more or less out of phase with the red. Probably on a computer is way better. But anyway, so here, again, our gamma is equal to 0.1625. And at this point, our ratio of omega to omega naught, it's out here at 2. I put it here, but it really should be further out at 2. So you can see that, actually, you can see these graphs here. It's coming down, and it should be well below 1, and it should be getting closer and closer to 0 here as you go further out for higher and higher excitations. Now that we've looked at forced vibrations with damping. We'll next look at forced vibrations without damping. And it is true we have talked about this a little bit because we talked about the same differential equation where our gamma here, our small gamma, our damping constant was equal to 0. So we have talked about this, but by specifically stating it equal to 0, we get a simpler form of the differential equation, and then we can write that equation, that solution, in another form that gives us some insight into some other natural phenomena. So here is our differential equation where we have our small gamma, our damping constant, equal to 0, so our u prime goes away, and here's the forced function. And so this is our general equation here. So it's much simplified from what we had with that other, the A with the delta and everything else. But what we can look at is first, the first case is when our frequency is not equal to our natural frequency. We can solve an initial equation to get our C1 and C2, and what we see is C2 will be equal to 0. So what we're left with is that U is equal to F naught M omega naught squared minus omega squared times cosine omega t minus cosine omega naught t. And this is one of the examples where I don't want to get weighed down with the calculations, but how I got to here, I kind of did over here for your reference. Also here, I just took out this green part and worked on it by itself here. I didn't want to carry the rest of the equation around. But what you can see at the end, which is what we're going to see on our next slide without all these ugly calculations, is that our u, where is it? Our u is equal to 2 sine 1/2 omega naught minus omega t times sine is 1/2 omega naught plus omega times t. Here I have summarized what we've done so far. First, we solved our second order differential equation. Then, when we assume that omega is not equal to omega naught, we use our initial conditions and we get C2 is equal to 0. So we have this so far. And then we did a bunch of algebra and some other trig functions, and we got that U is equal to 2F naught over M, 1 over omega naught squared minus omega squared times sine of 1/2 omega naught minus omega t times sine of 1/2 omega naught plus omega t. One's a plus, one's a minus. Other way around, one's a minus, one's a plus. And I underlined this because in your book there was a typo, and this omega naught squared minus omega squared was not under the 1, but it really should be. Now, when the difference between omega naught and omega is small, then this part here, this sine frequency, is going to be greater than this sine's frequency. So you have like a kind of more rapid sine wave oscillation going on inside a slower sinusoidal amplitude. So this periodic variation of amplitude is called a beat. And the graph looks like this. Again, there's a periodic, here we have our oscillation, but there's a periodic variation in amplitude as well. And I have an example for you. So if we solve u prime plus u equals 1/2 cosine 0.8t with the initial conditions u naught equals 0 and u naught prime is equal to 0, again, just comparing it to this form of our equation, m is equal to 1, k is equal to 1, our f naught is equal to 1/2. Where did I get omega is equal to 0.8? Oh, over here. I don't know why I put that before my 1/2. Okay, so our omega is equal to 0.8, and then we can also find our omega naught, which is square root of k over m, which is equal to 1. So now I can plug it into my equation that I have here. I have u is equal to 2 times f naught, which is 1/2, over m, which is 1, 1 over omega squared, which is 1, minus omega naught, which is 0.8 squared. That should be omega naught squared, and then all of this squared, so this should be a squared, times sine of, now I'm lost, sine of 1/2, 1 minus omega times t, sine of 1/2, 1 plus omega, which is 0.8 times t. And so when you do all the calculations, you get 2.78 sine of 0.1 t, sine of 0.9 t. And if you graph this, this is the exact, well, not, because my graph isn't very good, but if you graphed it, you would get this, you would get the exact solution, which my graph is an approximation of. So that was the beats. For the resonance case, shouldn't surprise you. Omega is equal to omega naught. And this is the form of our solution now. So when we solve u double prime plus u equals 1/2 cosine t, u of 0 is equal to 0, and u naught of 0 is equal to 0. So, gosh, I guess I solved it out by solving the homogeneous equation. And then I took y, since we have a cosine here, using our undetermined coefficient. Since cosine is g of t, then my y is equal to at cosine t plus bt sine of t, right? Because it can't be cosine t, because cosine t is already here in our general solution of our homogeneous equation, so we have to multiply by a factor of t. Then we take our y double prime, y double prime, and then we plug it into our equation, y prime plus y, and we get a is equal to 0, b is equal to 1/4. So our u of t is equal to c1 cosine t plus c2 sine t plus 1/4 t sine of t. Plugging in u of 0 equals 0, c1 is equal to 0, u prime of 0 is equal to 0, so c2 is equal to 0, which means our final solution, after all this work, is equal to 1/4 t sine of t, meaning the motion will become unbounded by this because of this t, as t goes to infinity, regardless of c1 and c2. So this is kind of what our solution will look like. And also, in reality, you probably know that the amplitude won't go to infinity because the spring force equation, Hooke's law, requires that u to be small. So by having, u at infinity, we're kind of no longer in this, probably the spring will be deformed or break or something. But we're no longer really, we're pushing the model beyond its limits. But this is just a second look. We had looked at this before, even when we looked at force vibrations with damping and we let damping go to 0. But this is just a second look at using this form of the equation. To summarize what we talked about in this video, we talked about applying a periodic external force to a spring mass system. And this was the second order differential equation we had, mu double prime, the mass m times u double prime, u being the displacement, plus our gamma, which is our damping coefficient, u prime, plus k, which is our spring coefficient, times u is equal to f naught cosine omega t. This is our external force. And we did not solve this, but I told you this was the solution. So the solution is equal to u is equal to r cosine omega t minus delta, where r is equal to f naught over capital delta, where capital delta is this square root m squared, omega naught squared minus omega squared, all of that squared, plus gamma squared omega squared. And then we also had a formula for our delta, our phase. Cosine of delta is equal to m omega naught squared minus omega squared all over delta. And we also had a formula for sine. And then we also had, just to remind you, our omega naught is our natural frequency of our spring mass system dependent on k and m, and actually is equal to square root of k over m. I had followed these 4 steps that we use to solve non-homogeneous second order differential equations, linear differential equations with constant coefficients. But and that's how we essentially got this formula here. But to get this formula from the equations here takes a lot of algebra. So this is suggested that you memorize this, or maybe you have a cheat sheet. We looked at this formula and we kind of investigated 3 different cases. First is when our forcing function, our f naught cosine omega t, when its frequency was much lower than omega naught, the natural frequency of the system. And we said after the initial transient response, that the initial transient response will damp out, and the remaining steady state response is essentially in phase with the excitation, and amplitude slightly larger, somewhat larger. And we had an example. This was our graph to go along with it, along with calculations. Then we looked at the resonance case, where omega is equal to omega naught, and the amplitude of the steady state increases many times the static displacement, and the phase lag delta was equal to pi over 2. And we had an example, and this was our graph, and these were our calculations. And then we did high frequency excitation, where we took our omega for our external force, and it was twice as large, but you can make it as large as you want, but it's twice as large as omega naught. And we observed the amplitude of the steady state force response is a fraction of the static displacement. And the phase difference between the excitation response is approximately pi. And this was we did an example, this was the graph, and these were some of the calculations. We did use this equation to look at behaviors as this gamma became very small. But we also went ahead and set this gamma equal to 0 so we could get the simplified equation mu double prime plus ku equals our f naught cosine omega t, and then see what that form of the solution could explain in terms of other different physical phenomena. And here is where we have the gamma equal to 0 and the simplified form of the differential equation mu double prime plus ku is equal to f naught cosine of omega t. This was our solution, our general solution that we found with regular methods. And then from here, we could use trig and some algebra to also convert it into this form. And this is the form that we use to analyze beats. So what you can see is if omega is not equal to omega naught, this sign, part of the sine wave, part of the solution, has a higher frequency than this part over here. So what we have is this we have this higher frequency sine wave, but within that, the amplitude is varying by sinusoidally. So we have this kind of oscillation within an oscillation. For our second look analysis, we used this equation here, and we took the forced frequency equal natural frequency. In other words, omega is equal to omega naught. And we saw that after we simplified, this was our general solution. We saw using our initial values that C1 and C2 would be equal to 0. And what we were left with here was 1/4 t sine of t. And what that tells us is because of this t, as t increases, then our amplitude and our motion will become unbounded. And so that's our idea of resonance here. Again, because forced frequency equals natural frequency. And of course, in reality, you're not going to have a spring that goes to infinite oscillations. But there's other things. One, the spring force equation with Hooke's law requires U to be small, relatively small. So we're to get to this unbounded motion is abusing our model, the spring force model. And that's it for this video. Thank you for watching.